Hi, good morning.
No.
Hi.
What's up?
Hello.
Please, guys, have a seat because we are starting. Okay. So, good morning, everybody. Online attendees and students in present. So, we start back with a series of courses given by this PhD program. So today it will be a 3 days lectures given by Professor Andrea Pau and Professor Patrizia Travalucci, which will start tomorrow. Yes. And Professor Travalucci is the coordinator of this PhD program, and Professor Pau, she's an associate professor of our department. She's involved in structural mechanics, structural dynamics, and all researches concerning mainly the topic of these lectures. This course's title is Ultrasonic Bulk and Guided Wave Propagation in Classical and Non-Classical. And I believe that will be very interesting. This is just this is the third or the fourth year that you.
The third. So every time I change things, so
it will be very.
It is still evolving.
It's very interesting. So before let Professor Pau start, just let me remind to all attendees that you cannot record this lessons online because we are providing the recording of this. So eventually, after we have the say approval of Professor Travalucci and Professor Pau, we will give you the video of the class. So please do not ask for recording this session via Zoom. We are doing that, as you can see, recording still on now. So this class does not provide any credit, but the PhD program could certify the hours that you spent here during this class. So please, Professor Pau.
Okay, thank you, Andrea, for your introduction. And first of all, I would like to tell you how this course is organized. You see here that I'll be lecturing today until 12, and this afternoon from 3 p.m. to 5 p.m. I will introduce the basic concepts of wave propagation in continua, but also in discrete systems. And this afternoon we will discuss reflection. I have changed some things which I will detail afterwards in my presentation. But anyway, this afternoon, basically, reflection between boundaries will be involved. And tomorrow, Professor Travalucci will introduce you to the main concepts concerned to the modeling of complex continua, which are endowed with additional degrees of freedoms or additional strain descriptors. And this she will be also lecturing on Friday, and on Friday the final lecture will be mine on the description of wave propagation in enriched continua, meaning second gradient continua and or Cortera continua. So thank you again for joining, and I will start my presentation. Just tell me if you can see my screen. Can you all see my screen?
Anna Maria, I believe you have to share your screen.
Okay, sorry. Yes, you're right. I forgot. Every time I forget it. Must be a sign. Yes, share. Okay. Is it okay right now? Can you see?
Yes, yes, yes.
Okay. Okay, thank you. Okay, so this is the updated program. Today I will present you something. I mean, this class is basically evolving. So each time I teach it, I study new things and I add them to the old presentation. In particular, this year I would like to present a completely new part, which is a connection between the dynamics of infinite degrees of freedom system and the corresponding continua. And I will try to do that both for like classical continua, for instance, think of bars or to strings, and to non-classical continua like second gradient or Coursera continua. Then I will move to the description.
In the online, we see the screen split this way.
Oh, sorry, I don't like it. How can I change it like that? No. Like that? Yes, I don't like it at all. No. Like that? No.
Ah, perché questo lo vede come il secondo schermo. Perché questo? Lo vede come il secondo schermo. Ah, questi siamo noi che parliamo.
Ok.
Ok. Non so così. Spero che o si mette modalità schermo. Forse così non vede.
Ok. Sì,
Okay.
better. Can you see it better right now? I mean, those ones who are online.
Yes, it's better now.
Okay, better. Thank you. Okay, yes, I was telling that then we will move to the description of the dispersion principles explained by means of waves, the propagation of waves in strings. And then today we will also present the bulk wave propagation in unbounded isotropic and anisotropic classical continua, and we will define what is the acoustic tensor. Finally, I will present a cube cutting technique for the experimental evaluation of material constants, which is basically an application of the propagation of guided waves in continua, and in particular in orthotropic continua. This afternoon we will discuss reflection, transmission, and refraction of waves from interfaces, and here we will be ready to present the guided waves in plates, the different kinds of waves in plates that might be shear and Rayleigh-Lamb waves. Then we will discuss semi-analytical finite element methods for the determination of the dispersion curves in waveguides, and also the forced response of a waveguide with the principle of reciprocity. This Friday, instead, as I told you before, we will study kinematics and dynamics of periodic discrete systems endowed with rotational degrees of freedom and at a distance actions, and we will see how waves propagate in this kind of continua together with the discrete to continuum transition. Initially, I had thought of presenting you also a couple of other topics, which are those ones are highlighted here in gray, but I don't think I will make it. And in particular, this is this concern the propagation of guided waves in non-classical waveguides and the nonlinear effects in wave propagation with the treatment of perturbation methods. So I think these parts will be for next year. So if you like it, just keep on following, because we will discuss new things. Okay, here I have listed some references, and in particular for the basics of wave propagation. The basics are those ones which I have highlighted in bold fonts, and are the book by Rose, which is the one I suggest everyone to start with, which concerns ultrasonic waves in solid media. And a very classical book is the book by Karl Graf, the second one, Wave Motion in Elastic Solids. But this book is a kind of, I don't like this definition, but let's say, quote, old book. So it's a sort of list of recipes. And while the book by Rose, I mean, if you have some doubt, go and check the book by Graf. If you want to have a wider picture, start with reading the book by Rose. Then there is the book by Old, Acoustic Fields and Wave in Solids. It contains many interesting aspects. In particular, the principle of reciprocity is explained very well in that book. And also it entails not only the propagation of waves in solids, but also the electromagnetic wave propagation. So if you have interests more in a multi-field or mechanical aspects of wave propagation, not only mechanical, but I mean more other phenomena that are not necessarily strain waves, like those ones we are discussing here, just check that book. Another book that I read recently is the book by Georgi, The Physics of Waves, which is a book which is used mostly by physicists. And I like it. I like it because it gives you a kind of a slightly different point of view from the approach of the engineering approach. Like some parts are more theoretical, so it's more theoretical, but it's also very like fundamental book. So it's a reading that I suggest. And finally, also in the book by Morton Gertin, An Introduction to Continuum Mechanics, there are some interesting explanations that concern, in particular, the acoustic tensor. And this is at the end of the, it's one of the final chapters of the book. I have listed some other books that are, this is something that remained from the lectures I gave last year, and I'm not sure we will say anything about those things, but anyway, you can check them if you're interested in some aspects that are the spectral elements or nonlinearities, or imaging, which is an application of waves. Imaging means imaging either of like something which is embedded in the structure, like a defect or an inclusion, or also the reconstruction of the three-dimensional reconstruction of a picture, because you, first of all, thinking of the first thing I said, meaning the reconstruction of some embedded inclusion, you can think of tomography of bodies, or the reconstruction of the presence of a defect inside the structure. All these objectives are reached by studying the reflection or the transmission of waves. And this is the same also with regard to the reconstruction of a 3D object with a set of pictures, because you've got to think that light emission is waves. So we can use the same principle to do many things. And in fact, this goes to the motivation of this class. So why should we study wave propagation? The main motivation is that being able to handle wave propagation is essential to applications in many fields. And in particular, I started studying wave propagation to understand non-distracting evaluation techniques. But then I understood that there are many more applications and waves and ways to use the wave response of a solid. I mean, you can understand many things. And in fact, non-destructive techniques enable to locate and measure, as I was saying before, to locate and measure defects in structure, but also to determine constitutive constants, but also to identify the state of stress. Moreover, the study of wave propagation can improve the understanding of many problems in vibration analysis. In fact, elastic wave propagation can handle both transient and steady-state vibration phenomena, which arise in the limit when time becomes large. Obviously, everything small or large has to be compared to the size of the phenomenon that we are observing, and to the size, not only to the size of the phenomenon, but also to the size of the structure in which waves are propagating. In fact, when we mention small wavelength with respect to what? With respect to the size of the object where waves are propagating. Remember that this is meaningful because ultrasounds are sound waves which we cannot, the human ear cannot hear. This means that the frequency is higher than more or less 20 kilohertz. So if you want to size defects that are very small, you might need to use higher frequencies than that. So we begin our study of wave propagation with the description of the transition between the dynamics of of a system made of infinite discrete particles. We will show how in the limit this can coincide with a continuum system. And in this way, we will be able to connect the dynamics of systems that are made. What's going on? Can you still hear me?
Yeah.
Yeah, okay. So I was saying that in this way, we will be able to connect the dynamics made of an infinite number of system of one particle systems, oscillators, to waves in strings and bars. I've used this approach because I think that many of you might be familiar with the oscillations of degrees of systems that are made like that. So let us start. Just let me get rid of that because, yes, maybe this is better. Let us start with a system made of n discrete particles of mass m. Each particle is connected by equal springs of stiffness k. A system like that, you see that the configuration of the system is described by n displacements. In this case, I have placed a left and a right boundary. If you extract the ith oscillators, you see that this is simply the free body diagram. A single at the ith oscillators has is subjected to the inertia force, which is this force in red, and by two elastic force, which are due to the action of the adjacent masses. If you write down the equation of motion, you obtain an equation like that, which reordered gives you something like that. Now you can think of writing all this in matrix form. And in matrix form, you see that the dynamics of the system is described in this way. You've got a capital K stiffness matrix, a capital M mass matrix, and a capital U displacement vector. You can immediately observe that the matrix M to the -1 times K, which is the matrix which enable you to find the solution of this problem, has a band structure. And the only non-zero elements are the diagonal element and the elements which are next to the diagonal on the right and on the left. This interaction is called local because you see that the ith element interacts only, you see, it interacts only with the I+1 and with the I-1. This is not the case when you have, for instance, second gradient interaction, because that one is what is called at a distance action. In that case, the ith oscillators, and I'll present you that this Friday, interacts both with the adjacent oscillator and with I+2 and I-2. That is the at a distance interaction. Okay, so in the presence of a local interaction, you've got this nice matrix with a band structure. Now, you're probably familiar with the calculation of the normal modes, which are the eigenvectors of this matrix. But there is a more general technique which implies separation between the oscillators and the boundaries. And to apply it, we have to consider an infinite system with no boundaries at all. And in this case, if we remove the boundaries, we have an infinite assembly of masses just connected by strings. And the idea is that this system looks exactly the same if it is translated to the left or to the right by a multiple of the unit module, which is this distance, let's call it distance A. It's actually the module size. You can do whatever translation you want, provided that this is an integer multiple, integer plus or integer minus, of the size of the modulus. And unfortunately, we see that this phenomenon is described by an infinite number of degrees of freedom, and unfortunately by an infinite matrix. So the M-1 times K matrix is no longer finite, as we saw before. So what can we do? In fact, we said, okay, actually, if I pick up a finite number of particles and translate it of a finite number of moduli, this can be expressed by a matrix like that. This is called the symmetry matrix, and this idea is called translation invariance. The symmetry matrix, S, capital S, is an infinite matrix that just moves the j+1 block to where the j block used to be, or vice versa. It is just, in this case, just a matrix with ones along to the next diagonal terms. You can use it both ways. If you make some simple calculations and you play games with this matrix, you observe that all these relations hold. But also, you see that if capital phi is an eigenvector of that infinite matrix, which you cannot calculate, but we will get that after. If that is an eigenvector of the system, also phi prime, which is S times phi, has to be an eigenvector at the same frequency. Obviously, you've got to do some algebraic manipulation, but you can get it. It's quite easy. I reported that here. And now let's give a look at the eigenvector of this matrix. They are the vector A, which satisfy this relationship. If you pre-multiply by m minus y times k, you get that. And it means, in the end, if you can find that if capital A is an eigenvector of S, I mean this one, if this one has to be satisfied, thanks to the symmetry, also m minus 1 times ka is an eigenvector of the symmetry matrix. Then you basically, and moreover, I've got to add something something extra. If the eigenvector, sorry, this is eigenvectors, not eigenvalues of S are all different, then m minus 1 times k has to be proportional to the eigenvector of S. So also this capital A is an eigenvector of m minus 1 times k. So what is the game here? Basically, instead of searching for the eigenvector of m minus 1 times k, which we cannot how to do that because we don't have the mean to invert an infinite matrix, we search for the eigenvector of that very simple translation matrix. And this might seem to be a bit not very meaningful because, okay, you just changed the problem. Instead of finding the eigenvector of m to the minus 1 times k, you're searching for the eigenvectors of A. Yes, but finding the eigenvector of S is really easy, and you will see how you can do that. In practice, the translation symmetry enables us to say that if this beta is an eigenvalue, the jth term of the translation matrix is just the eigenvalue to the jth power. If you're interested, you just do these substitutions, and then you find that if you pick up this eigenvector and substitute in this equation, you derive a dispersion relationship, which is this one. Then you've derived, with this trick of searching for the eigenvectors of the symmetry matrix, you have derived this equation, which is the dispersion relationship of the infinite system. Now, let us assume that you don't know what is the value of beta. But you can write whatever number in form of an exponential. You pick up this beta and you write it as an exponential like that. You substitute, and then you come up with this nice expression. you use the Euler's formula, and this reduces to this other one, and in particular, oops, sorry, to that one. To that one. Now, another step. Assume that A is small. So you are moving toward a continuum system. The size of the module is small. Then you get that. But look at that. K times I, A, is just the stiffness per unit length. If you have a bar, this is just E, Young's modulus, times A, the area of the cross-section. And A over M is just the inverse of the mass density per unit length. So this relationship, this one relationships, becomes the classical dispersion relationship of a bar, that is a continuum system. So with this trick, you can move to continuum system also in much complex cases. And moreover, another thing you can do is that you pick up the equation of motion, the one we wrote before we wrote the balance for a single oscillator of the infinite system, and we make it continuum using Taylor series. This gives that, and again, you obtain that, but this is the equation of motion of the bar. And obviously, it coincides with that dispersion relationship, but when we substitute here, and we will see that this is a general method to search for, to determine dispersion relationship. If you substitute here a solution, which is called a tentative solution, which is a harmonic form in space and time. Okay, now that I have shown you how we can move to systems of discrete particles to continuum system, I would like to present you some concepts that concern just the continuum system. And I will start to a case you probably already know, which is the taut string. What is the taut string? You consider an element of infinitesimal length, which is a part of an infinite string subjected to a tension F. You assume that the horizontal displacements are negligible with respect to the vertical deflections, so you do some approximation, and you come up with this free body diagram, where this is the tension, which is constant through the string, and you've got here the inertia, and theta is the deflection angle. You write down the balance of inertia and other forces acting on the string, and you consider the case where no external forces are applied, like P of xt is equal to 0. And you obtain this equation, which, as you see, yes, delta theta, yes, which, as you see, has exactly the same structure. I guess there is a mistake here. I've got to double check it. Something does not convince me. Anyway, this is correct, because in the end, you come up with exactly the same relationship you had before. Just yes, let's say this one, which you had for a bar. And as you see, this is a second order hyperbolic homogeneous because there are not external forces, partial differential equation, which can be written also in this other way, where C sub 0 is called the velocity of wave propagation. Now, this C0 is the square root of the tension divided by the mass density. And you see that the wave propagation speed increases with the tensile when the tensile force increases. This is a phenomenon that probably every one of you has experienced when you pluck a guitar string. When you increase the tension, the pitch becomes higher. And this is obviously the guitar string is not infinite. It's like a sort of it's on two supports, but you will see afterwards that this connects to the wave propagation. So the two phenomena are connected. Now, a classical way to solve this this equation is separation of variable, which leads to the two solutions that can be written in exponential form like that. And these waves, this solution represent harmonic traveling wave. You see that you've got a part here which represents waves propagating rightward, and a part here which represents waves propagating leftward. If you use Euler's formula, you can do some calculations and express the previous expression in terms of trigonometric functions. Now, I have depicted this solution either in space at two time instants. This abscissa is x, that is space, or using the function time at two different points in space, and you see that they look exactly the same. But if you observe what happens in space, the distance between the two crests is the wavelength. It's what is called lambda wavelength, which is the inverse of the wave number, is 2 pi divided by the wave number. The wave number is, in practice, the density of wavelength in space. Instead, if you check what happens in time, the distance between two crests is the period, which is 2 pi divided divided by omega, the frequency. So you see that there is a duality, space-time into wave number, frequency. So they correspond. And in fact, this duality can be used to obtain dispersion relationships. How can you do that? You got a model. You solve it. You've got the solution expressed from a finite element model in time and space. You can pick up the solution at whatever point and whatever time instant. Now, if you pick up all the solution in all the points, you've got a sort of matrix of time histories in space. You do a two-dimensional Fourier transform and you get the dispersion relationship. I will show you better after, in this lecture, what is exactly a dispersion relationship. But anyway, this is the technique. Now, let's go back, yes, to this solution. If you pick up this solution and you substitute here, which means that you want to know which kind of harmonic waves can propagate in this system. Just pick up this, substitute here, and you get what? You get that, the characteristic equation. Already found it before. Now let's check this exponential. This exponential is called the phase angle. And basically the propagation velocity of waves, which is this c sub 0, which is square root of t divided by t, is, which we called wave velocity, is nothing but the velocity of the constant phase angle. Why? You pick up two phases at two time and space values, two different, t sub 0, sorry, x sub 0, t sub 0, x sub 1, t sub 1. You check out what happens when these two quantities equal phase are equal, and you get that the ratio between space and time is the phase velocity, which is omega divided by k, which is t sub 0. So this c sub 0 is actually the phase velocity. What is the phase velocity? The phase velocity is the velocity at which a given wave of a given frequency propagates in space. This is the phase velocity. Remember that. How do we express the properties of waves in terms of phase velocity? They are basically summarized in the dispersion diagrams. I mentioned them before. Dispersion diagrams can be two different kinds of diagrams. They can be either wave number as a function of frequency, or vice versa, or phase velocity as a function of frequency. Now, in the case of a string, you see that this one relationship, k omega, is that one. So, k varies linearly as a function of omega. So you've got a straight line. The phase velocity, instead, is just the ratio between omega and k. And it is a constant, so you've got a straight horizontal line. The waves, the waves that have these properties, constant wave velocity, constant phase velocity, straight line, straight horizontal line, like that one, are called non-dispersive. Okay? The property of this kind of waves that are non-dispersive is that they do not distort while they propagate in space. What does that mean? This is space, this is an animation, you got a given wave, whatever wave, the same. It moves, nothing changes. This is not always the case. But before moving to dispersive waves, I would like to tell you, to make you notice that up to now, we have not enforced boundary conditions, okay? No boundary conditions. If you enforce boundary conditions, waves can be reflected at the boundaries, so that the waves propagating rightward and leftward can interact with each other. In many cases, this gives rise to what? To standing waves. And at the same time, the frequency is no longer undetermined, meaning that whatever free oscillation at whatever frequency can happen, but the structure can oscillate only at discrete frequencies. And these are the mode. The mode do exist. The modes of the structure, the natural modes of vibration do exist in a structure just because there are boundary conditions. So the spectrum, this one, is no longer continuum, but it is discrete. This is free oscillation that can happen at whatever frequency. Obviously, even a bounded structure can oscillate at whatever frequency, but you have to force it, okay? Otherwise, freely, it can just oscillate with its own natural frequencies. And this is a kind of mode. What does that mean? You see that the kind of oscillation is pretty much different from before, because before we had that in space, the phase changed. In fact, we had a phase velocity, a velocity of propagation of the phase. Here, the phase oscillation between 2 points is constant. 2 points can oscillate either in phase or out of phase. No other possibilities. And this is due to the presence of the boundary conditions and to the interaction between reflected waves. Okay, so we have seen the wave propagation in non-dispersive media. And I would like to consider right now a slightly different problem, which may involve distortion of the propagation disturbance. So consider a string which is no longer free of oscillating as it wants, but it's supported on an elastic base. Imagine a system like that. In that case, the one-dimensional wave equation has an extra term, which is due to the elastic force on the base. Imagine that the string moves down and the spring impresses a force which is directed upwards. And we do exactly as we did before. So we check out what are the possible conditions for the propagation of harmonic waves. So we pick up exactly the same solution and we plug in here. Okay? If we substitute here, we get that. So we see that we have non-trivial solutions only if this part of the solution is equal to 0. So this one is the new characteristic equation of the system. If you solve it, for instance, if you solve as a function of k, you derive this solution. So you see that this time k is no longer always real. Real k, remember, real k means propagating waves. But you see that if the ratio omega square divided by c sub 0 square is greater than the ratio k over f, k, capital K is the stiffness of the string. In that case, k is real. And we are exactly in the situation we were before. So we have just waves propagating rightward and leftward. But if the ratio of omega square and c sub 0 square is smaller than k over f, k, which is the wave number, remember 2 pi over length over lambda, the wavelength. In that case, you got non-propagating waves. Why? Because k is imaginary. And if you plug in here something that is imaginary, it multiplies by I, and it gives a quantity which dies out in space. These terms are called evanescent or ringing terms. They are not even harmonic. These are just waves that disappear after a given spatial span has elapsed. Now, the dispersion diagram looks like that. Dispersion diagram, remember, wave number as a function of frequency. You can represent the dispersion diagram in this case as a diagram where you report in the abscissa omega, and in the ordinates on the upper part you report the real part, on the lower part you report the imaginary part. So you see that there is this part where k, as we said before, is imaginary. Then when omega increases, is larger than a certain value, k becomes real and the waves start to propagate. This frequency is called cutoff frequency, and in this case has exactly that value. Now you see two things right now. First thing, I mean, with this very simple model, we can observe two things. First thing is that not all solutions can propagate in space. Second thing is that if we observe the phase velocity, which is the ratio between omega and k, this has this form. So if you report the real part of the phase velocity as a function of the frequency, you see that the phase velocity is no longer constant as it was before, but it is a function of frequency. And in particular, you can see that there are some values of omega when the phase velocity goes to infinity. What does that mean? That the waves cannot propagate. Now, when the phase velocity varies as a function of frequency, there are consequences on the maintaining of the shape of the disturbance as it travels in space. because the different the different frequencies travel at different frequencies, so it's a mess. So the result is that a disturbance does not longer remain unaltered when it travels in space, but it changes. So what you observe is something like that. These crazy things, which frequently are also accompanied by attenuation. Attenuation is not the same as dispersion, okay? Dispersion is just the change of the phase or the group. We haven't seen what is the group velocity as a function of frequency. Attenuation is attenuation, which is tied to damping. Another concept. Are you tired? Do you want to take a break? 5 minutes? Yes, 5 minutes. Non va bene? No, non ho capito.
Ci sta
recording. Okay, now the recording is going on. Okay. I hope so. Spero di sì. Condividi schermo. Yes, I'm sharing right now.
Yes.
Okay, can you all hear me and see my screen?
Yes.
Okay, so let's start the second part. So a second concept I wanted to discuss with you, besides the phase velocity, is the group velocity. The point is that when you have a wave which contains just one frequency, which is called a monochromatic wave, no problem. It propagates with phase velocity. But unfortunately, reality is not that simple. And it's very frequent that you have wave packets. Wave packets containing a given frequency bands. And unfortunately, they don't travel at the phase velocity. Not only they don't travel each one at the same, but the whole packet doesn't travel at the phase velocity, but at the group velocity. And this phenomenon can be explained if you consider two waves with slightly different frequencies and wave numbers like that, propagating in the medium. And you do some trigonometric manipulation and you come up with a relationship like that, which is made of a blue part, which is a low frequency term, and the high frequency term. The high frequency term has wave number, which is the average wave number, frequency, which is the average frequency, and the low frequency number, which has a wave number and a frequency which is K1 minus K2 divided by 2, the difference. Then this results in this phenomenon, which I have depicted in this animation. You've got two waves, slightly different in phase and, in wave number and frequency. The blue wave, you see the dot, which propagates at the speed of the blue wave. The purple wave, you've got the red dot, which propagates at the speed of the purple wave. But if you mix them, if you do superposition like that, you get that. The sum of the frequency, this V of xt, this one, is why are you not working? Sorry. Yes. The sum of the frequency is this gray wave. And you see that the envelope of the gray wave moves at the third velocity, which is the velocity of the envelope. And it is the velocity of this low frequency term. In fact, you see that the envelope stays behind the two other waves. So this one moves at the velocity, which is the ratio between delta omega and delta k. And this, in the limit, gives you the derivative of the frequency with respect to the wave number. So this ratio here. And this is very useful to have this one, because you can pick up, if you have, for instance, a relationship that you know, like in that case, you have an analytical dispersion relationship, you just calculate the derivative of one with respect to the other, and you get the group velocity. Okay, things might be much more complicated than that, because we have shown the dispersion relationships for one-dimensional systems, either the taut string, which is non-dispersive, or the string supported on a bed of springs. But I will show you that if you have a plate, for instance, the dispersion relationship look like that. So you no longer have one curve. For each frequency, you have more than one curve. And each one of those curves is called wave mode. It's a mode, it's a wave mode, it's a mode that propagates in space, but it's a mode which involves not the whole structure, but only a piece of the structure. For instance, the cross-section. Why? Because the cross-section has boundaries. So you have something which is in between modes. Locally, it's a mode on the cross-section of the plate. But since you are not intersecting the whole boundaries of the plate, you don't see global reflections. So that is a wave mode. So you see how this is complex for a plate. These are called Rayleigh-Lamb waves in a plate. And this is the picture. This is a picture of their phase velocity. You calculate the derivative, and you get that other diagram, which is the group velocity. A group velocity where there are different modes, each one moves at a different speed. You see some of these modes going to infinity. What does that mean? It means that for frequencies lower than some cutoff frequencies, you don't see those modes. You can't see those modes propagating in the plate. You can see them, but it's very difficult to observe them experimentally or numerically. You can see them just locally. Why? Because they serve to satisfy boundary conditions. So they exist, but they are like that. They are here. They have imaginary wave number. They are evanescent or ringing terms. You don't see them in experiments because they die out very, very quickly in space. So I would like to show you the last example, because we've seen just two cases when wave numbers are either real, propagating waves, or imaginary, just ringing terms, evanescent waves. There is something which is in the middle. So you can even have complex wave numbers. Complex wave numbers are solutions that are oscillatory in space and time, but whose amplitude dies out in space. It reduces in space. They emerge if in your term you add a viscous damper. So some materials are characterized by dispersion, variation of this wave propagation speed, and attenuation as well. And this is represented by viscoelastic devices like that. A viscoelastic device reacts with to velocity, to displacement, and in particular to velocity, with a force which is proportional to displacement, K, and to velocity 2. This is a viscoelastic device. And if you plug in the force which opposes to motion of, in this case, you get a relationship which is like that. You get two extra terms. One which depends on displacement, as before, and one which depends on velocity, a new one. And what do? Exactly the same. You pick up a tentative solution, you substitute in the equation of motion here, and you get a characteristic equation. You see that this characteristic equation looks like that. So it's got this piece, which is imaginary, and this part, which can be either real or imaginary. And in all cases, all cases, you always have an imaginary term. So in this case, you've got either just imaginary wave number or complex wave numbers that are have either an imaginary part and a real part. So they propagate in space, but with a decaying amplitude. And I made here a list of all these complex beasts which we have. Some are non-dispersive, some are dispersive. So, non-dispersive waves, just a list. One-dimensional systems, when we observe non-dispersive waves, when we have rigid cross-section, what does that mean? Whatever cross-section can behave as rigid at low frequencies. When you go to high frequencies, since high frequency means small wave number, small wavelength, it means that the wavelength is the same size as the characteristic size of the cross-section. And when you are in those kinds of field, when the characteristic size of the cross-section equals the wavelength, then unfortunately the cross-sections appear as deformable with respect to the wave, and you observe dispersion. This is for axial waves. But for bending waves, they are always dispersive. I didn't add, I'm not speaking about bending waves. I'll do that next year. I will add a part on bending waves. But they are unfortunately always dispersive. Observing waves propagation in a beam is a mess. I hate it. It's really, really difficult because, yeah, dispersion is a mess. There are systems to treat it, but it's really difficult. Okay. Two-dimensional systems like plates. Low frequencies, you've got axial waves, they are called S0 waves. They are non-dispersive. Or another very nice mode is this SH0 mode. This is a shear mode. Shear waves, there is just one very nice wave mode, which is SH0, which is not dispersive. Then three-dimensional systems. Three-dimensional systems, they are always non-dispersive. Pressure waves, shear waves, very nice. They are non-dispersive. Dispersive waves are everywhere in all these other systems. One-dimensional systems with deformable cross-sections, meaning high frequency, all waves are non-dispersive. Two-dimensional systems, high frequency shear waves in a plate, besides the SH0 modes, and high frequency axial waves, symmetric waves, non-symmetric waves. Non-symmetric waves are actually bending waves. Yes, please.
You mean that in three-dimensional system, all the shear waves are non-dispersive?
Yes. If the system is homogeneous, you have non-dispersive waves. No, in the plate, just SH0. It's the only mode which is non-dispersive, or symmetric waves, or also asymmetric waves. No, asymmetric waves, sorry. Asymmetric waves are always dispersive. Just symmetric waves are non-dispersive at low frequency. Okay. Now let's move on. Sorry, are there questions? Or maybe you want to ask at the end of the lesson? I don't know. People, guys who are online, is it okay? Can I move on to waves in unbounded solids?
Yes, we can ask at the end.
Okay, all right. So let's move on to waves in unbounded solids. I have prepared here some slides for either homogeneous and isotropic and anisotropic materials. Okay, so first of all, some names. Waves that propagate in unbounded. No boundaries at all, no surface, nothing that can cause reflection of waves in three-dimensional waves are called bulk waves. And as you know, it's always a matter of size, because a structure can be considered, when can it considered an unbounded medium? When wavelength of the propagating waves is small with respect to the size of the structure. So big structures, bulk waves. We will consider the case of isotropic media first. And in this case, the equations of motion for a homogeneous, isotropic, linear, elastic solid for infinitesimal displacement, and yeah, the story, same story, and in the absence of body forces are something like that. You know that there is a linear relationship between the stress, sigma, this sigma is the stress tensor, and capital A is the strain tensor, which is something like that, where mu and lambda are the Lamé coefficients. They are used to characterize the material. Capital E is the strain tensor, and it is related like that to the displacement field. Is the symmetric part of the gradient of the displacement field. There are some identities of tensor analysis. If you pick them up, you use them to substitute and to get from here a differential equation where the displacement field appears. You get something like that, and this is usually called the Navier differential equation of motion. It is an equation of motion where derivatives with respect of space and time of the displacement field appear. And what do you do? Always the same thing. You want to know what are the conditions under which harmonic progressive wave can propagate in the solid. But this time, your solution is a vector, is no longer a scalar, because the configuration of each point is described by 3 components. So the displacement field is done like that. We've got an A, which is an amplitude, which has 3 components. But this A is multiplied by an exponential, which is made like that. The exponential, okay, time, luckily, is one-dimensional. Frequency, luckily, is one-dimensional. But space is 3-dimensional. So, also the wave number is 3-dimensional. Then here, it appears the product of a vector. So the wave number right now is a vector, is no longer a scalar. And here you get the scalar product between the wave number and x, the spatial coordinate of the point. This is a 3-dimensional, this k vector. Because you know that this time, in 3 dimensions, the wave can propagate wherever in space. So, actually, this 3-dimensional wave number is nothing but a scalar k times n. What is n? N is the normal to the wavefront, which can span all space. So you can either express k, the k vector, in this way or by its component. So remember, this n, this bold n, is the normal to the wavefront. And this solution expresses plane progressive waves that are waves with a plane wavefront. Okay? K is just the modulus of the wave number, and it's obviously the square root of the sum of the square of its component. Now, as I told you, you do exactly the same as you did before. You pick up the solution, you plug it into the Navier equations. Unfortunately, you've got to do some algebra. I have reported it all here because this was really heavy to calculate, but you get it. You've got an easier life. You plug in here and you get this equation, this nice equation, which is the equation which describes under which condition plane progressive waves can propagate in an unbounded, homogeneous and isotropic solid. And this equation, if you extract A, which I remember is the amplitude of the wave vector, can be expressed in this other simpler form, where capital A is the acoustic tensor. This is called the acoustic tensor. And basically, you have recovered here an eigenvalue problem, because waves can propagate in this continuum only if c squared and A are respectively eigenvalues. C is again the square root between omega and k, phase velocity again, if they are respectively eigenvalues and eigenvectors of the acoustic tensor. So now the game is finding eigenvalues and eigenvectors of the acoustic tensor. But we are lucky because there is a theorem which ensures that if you can decompose a tensor in this way, and you can, some algebraic manipulation, you can decompose it like that. This is called spectral decomposition. And this nice spectral theorem ensures that a harmonic progressive wave with velocity c is an eigenvalue if it is equal to the square root of lambda plus 2 mu over rho, or to square root of mu over rho. Now, it is nice to observe that this spectral decomposition is made like that. You not only can easily find eigenvectors, but you can also easily find eigenvalues. And in particular, if you pick up this eigenvalue, in practice, you have a longitudinal wave, because A, the scalar product of the amplitude to n, is just equal to the modulus of A. And in this case, it results that displacements occur in the same direction as the direction of wave propagation. And you've got just one eigenvector, because this one is spanning a line, okay? This means that you are spanning a line, the line which coincides with the normal to the wave front. This other object is spanning a plane. This object is spanning a plane which is orthogonal to the direction of wave propagation. So what that means? Does that mean? It means that in this case, the displacements occur orthogonally to the direction of wave propagation. And in this case, you have two eigenvector because they have to span the plane orthogonal to the direction of wave propagation. In this one case, the wave is longitudinal. These waves are also called P waves. In this second case, the wave is transverse. And this second kind of wave are called shear or S waves. You see that here the velocity, which is the phase velocity, does not depend on frequency. These waves are non-dispersive. I have prepared here an animation which shows you what is the appearance of shear waves. You see, you've got displacement orthogonal to the direction of wave propagation. Okay, now I would like to move to the anisotropic solids. Anisotropic solids are a bit more complicated, and because there are more constitutive constants. It's a mess of constitutive constants. So it's not so easy to treat the equations of motion in tensorial form as we did before. So in the case of the anisotropic solids, what is called indicial notation is preferred. So pick up your pen, you write down equations, exactly as before. You get the Navier equations, pick up the solution, again, unfortunately, this time by components. I may have to make a change here because I'd like to change alpha with n just to be consistent with the previous notation. So you've got your solution, you substitute in the equation of motion, and again you obtain an eigenvalue problem, and you get this equation, which is again the characteristic equation, which has to be satisfied for waves propagating in an anisotropic solid. And this is the most popular expression of the characteristics equation, which is called Christoffel equation, this red one. Christoffel equations. Okay, again, also here, you'd better consider the wave number by components. You substitute, and you are also able, in this case, to extract the acoustic tensor. The acoustic tensor has components gamma, IM. Okay, it's a bit more complicated, but it's nothing different from the previous case. Not very different from the previous case, but one of the differences is this one, that right now you can no longer obtain that nice decomposition you've got here. You can no longer use the spectral theorem, and you can no longer say that waves are just longitudinal shear waves and just go home with that that idea. Unfortunately, here waves are mixed. They have both longitudinal and transverse components. And the solution, in this case, these are the eigenvalues are expressed in this way. This is an example I picked up from this paper. So these are called slowness surfaces. These slowness surfaces, because, okay, go back here. You've got, despite the fact that the problem is much more complicated, you still have got 3 roots, okay? But 3 roots for what? 3 roots for each direction of propagation. 3 roots for each direction of propagation. So these 3 diagrams represent the 3 roots for all the possible direction of propagation in space. And in particular, they represent the inverse of phase velocity. In fact, this is a reason because they are called slowness, which is the inverse of speed in practice. So each direction, you report the inverse of speed in that direction for the 3 different modes. And this time, the wave modes, also the components, are just mixed, okay? You don't, it's very difficult to express them in plots. Application, just 5 minutes to present you an application of materials characterization, then you're free. Okay, let us consider the anisotropic solid and how we can use waves to determine the elastic constants, because characterizing a material means that you want to determine the elastic constants, those ones that appear in that relationship between stress and strain. This is the most common goal of material characterization. Obviously, you can have other objectives, like, for instance, characterize determine density or stress, anyway, whatever. But let us now focus on the determination of the elastic constants. Okay, the determination of elastic constants in general is a nearly impossible task, because the tensor, which describes that relationship, has 81 components. But we are lucky. We are lucky because there are some symmetries. These symmetries concern either the stress tensor and obviously of non-polar media, and of the strain tensor, which are the congruence equation. The first ones are the equilibrium in terms of rotations, so that if you consider these additional equations, you can obtain some constraints. Therefore, you can reduce the number of constants to be known. And in particular, if you assume that materials admits a positive definite strain energy function, you can add even more constraints, and in the end you come up with passing from 81 to 21 elasticity constants, which is still a bit hard. Sometimes we are lucky and we have an isotropic medium. In that case, just 2 elastic constants. Sometimes we are less lucky and we have orthotropic media, but we can still find our wave. So, an orthotropic medium has a constitutive matrix, which is something like that. So if we plug this in the previous equations, also here I have used again n, but before I had used alpha, sorry about that, I'm going to correct this, but anyway, these are the director cosines of the wavefront. If you substitute in that previous equation, which is this one, the characteristic equation, you see that we are able to limit the appearance of these these constitutive constants in the characteristic equation. And in particular, if we consider a wave propagating along x1, we have these nice relationships which tie the velocity of the 3 waves, which are, as I told you, kind of a mixed wave, but you will see 3 waves appearing. These nice relationships relate the velocity of these 3 waves propagating along x1 to the constitutive constants. Okay? And other nice relationships that tie the propagation of these 3 waves propagating with a wavefront which is orthogonal to x2. So with 2 orthogonal waves to this axis, which are the principal axis of the of the constitutive tensor, you can determine these constitutive constants, all these 5 constitutive constants. Then, if you pick up a wave which is directed with an angle of 45 degrees, you also determine this yellow term. And again, you are missing these other terms, but you can derive the blue one with a wavefront parallel to, normal to x3. These are the blue one. And this, the light blue ones with a wave which forms an angle this is parallel to x3 and forms an angle with x3 and x1, and finally another wave which forms an angle with x3 and x2. And in the end, this is a procedure which is used to characterize an orthotropic medium, and this is called cube cutting technique. And it is often used to characterize crystals that have this orthotropic, often to find crystals that have these orthotropic properties thanks to the regularity of their internal structure. And this method is quite established, and it can be very accurate, and its results are very near to those measured with static tests. Obviously, one major disadvantage, but this concerns also static tests, it's its destructive nature, because it's done by extracting like pieces of small parts of a crystal, from the solid and extracting some samples that have different angles with respect to the axis of the reticulum. Okay, yes, just a minute. This is the end of this lecture, perfectly in time. And that's, yeah, thank you for listening. Yes, there is one question from the audience.
We need to cut the tube because it's difficult to send a wave through just like
yes, to all those directions, also because you've got angles and you've got boundaries, and you know what happens with boundaries if they, especially if they are not regular. You imagine sending a wave through an angle, a big piece through an angle. That's difficult. Okay.
Also, the type of waves.
The type of wave, I actually don't have experience in this kind of tests, but let me think. Yeah, in general, you should be able to excite all these three waves, but since in that case of in that kind of material, they are mixed waves. If you just choose one frequency, you should pick them up all with just one frequency, because they have components through the different axes. Okay. Questions from the audience? Okay, if you're okay, you can even ask question later today or later after the end of the class. No problem. So I will stop the recording, and I'll see you at 3 p.m. Okay? See you then. Bye-bye.